Bismillah Rahman Rahim. Assalamu alaikum. Welcome to ASTC. This is Cambridge A Level Mathematics 9709 Pure Mathematics 3. So today we'll be working through May June 2021 paper 32. All right, so let's get started. All right, so question number 1 is solve the inequality modulus of 2x minus 1 is less than the modulus of 3 times is less than 3 times the modulus of x plus 1. Okay. All right, so you can notice that there is modulus on both sides of the inequality. So here what we do is there is modulus on both sides, so we will square both sides. When you square both sides, then whether this part was minus or positive, it will still have the same square value. Okay, the square number that will turn out will be the same. So therefore, we can now remove the modulus and we will simply square it. 3 square times x plus 1 square. Now we can just solve this inequality. So this will be 4x square minus 2x minus 2x plus 1 is less than 3 square will be 9. Then we have x square plus x plus x plus 1. Okay. Then this becomes 4x square minus 4x plus 1 is less than 9 times x square x plus x, that is 2x. So 2x times 9 will be 18x, and 9 times 1, that is 9. Now we will move all of these terms on the left hand side towards the right hand side. So this becomes 9x squared plus 18x plus 9 is greater than oh sorry, my bad, let me write the values. Minus 4x squared plus 4x minus 1 is greater than 0. So 9x squared minus 4x squared, that will be 5x squared. 18x plus 4x, that will be 22x. And 9 minus 1, that will be 8, is greater than 0. So now we have to see if this can be factorized. So 5 times 8, that is 80. So if we look through the factors of, 5 times 8 is 40. If we look through the factors of 40, so what we can see is that 20 times 2, that will give us 40, and when we add them, they will give us 22. Okay, so 5x squared plus 20x plus 2x plus 8 is greater than 0. 5x is common, so we will have x plus 4 plus 2 is common, so x plus 4 is left. Then we can take x plus 4 common, and we have 5x plus 2 greater than 0. Okay, now in order to solve this, okay, we need to find the critical values. Okay, we need to find the critical values. So for critical values, what we'll do is we'll say that x plus 4 and times 5x plus 2 is equal to 0. So x is equal to minus 4 and x is equal to minus 2 upon 5. Now here we'll draw a straight line. So you can see that one of the values is going to be minus 4 and the other will be minus 2 upon 5. So we need to look for the inequality where your y is greater than 0. Okay, so the y part will be greater than 0 above the axis. Okay, so this is horizontal line, this represents x-axis, right? So it will be greater, the y value will be greater when it is above the axis. So in terms of inequality, that would be that when x is less than minus 4 and when x is greater than minus 2 upon 5. Okay, so that will be the answer to question number 1. Question number 2. On a sketch of an Argand diagram, shade the region whose points represent complex numbers z, satisfying the inequalities z plus 1 minus I is less than or equal to 1, and argument of z minus 1 is less than or equal to 3 upon 4 pi. Okay. Now, you should know that your complex number, when it is inside modulus, is represented in this form. It has to be in this form. Okay. So if it is in this form, that means that the required coordinates will be a comma b. All right. So you can see that this is not in this form. So first we have to rearrange it so that we can rearrange this complex number, this modulus, okay, in this form. So what we can do is we will say that we'll take minus common. So we will be left with minus 1 plus I. Okay. Now you can see clearly that this is the exact same form as written here. This is less than or equal to 1. Now, what does this mean? Now, you should be able to translate the modulus into words so that you understand what this expression means. This expression means that the distance of z, okay, the modulus basically tells you the length or the distance, right? So, distance of z, negative sign means from, and minus 1 plus I. So, these are the coordinates. So minus 1 is the x coordinate and I, that is the y coordinate on the imaginary axis. So we have minus 1 and 1. The distance of z from minus 1 comma 1 is less than or equal to 1. When you have this type of inequality, when you have this type of situation, then this complex number or this modulus, okay, represents a circle whose center is at minus 1 1 and whose radius is equal to 1. Okay, now that is the first part of this inequality. So we know that we have to draw a circle, okay, whose center will be minus 1 1 and whose radius is going to be 1 unit. That's the first part. Let's come to the second part. Here it says that argument of z minus 1 is less than or equal to 3 upon 4 pi. Again, this argument of whatever is inside the bracket should also be in this form. So I'm going to write it in this form: z minus, this will be 1 plus 0 I, because there is no I. So we're going to say, because there is no I, right, there is no y coordinate given here, that means it will be 0. So this is less than or equal to 3 over 4 pi. Now first I have rearranged it in the required form. Now what can I understand from this statement? So what I can say from here, argument of z basically means the angle of z. Again, minus means from 1 comma 0 is less than or equal to 3 over 4 pi. Okay, so on the left hand side, the locus which is represented by this inequality is a circle. The locus which is represented on the right hand side is a straight line. Okay, and that straight line has a center at 1 0. So you're going to draw a straight line from here. Okay, so let me show it on the axis over here. So first let us label. This is the imaginary part of z and this is the real part of z. So this will be 1, 2, 3, minus 1, minus 2, minus 3. Then here we have I and here we have 2i. Okay, then over here this is 0. This will be minus I and this will be minus 2i. Okay, all right. So the first one was a circle with center minus 1 and 1. So first I'm going to mark the center, minus 1 1, that will be here. After that I'm going to draw a circle whose radius should be exactly 1. Okay, now here this is not just a sketch. Bear in mind, this is not just a sketch. Okay, how you're going to draw this is by using a compass. You have to open your compass to 1 centimeter, okay, to 1 unit, and all of these values with that you mark on the axis should be accurate as well. So let's say if you have taken 2 centimeters to represent 1 unit, then the rest of them should also be 2 centimeters apart. Okay, so what I'm trying to say here is that this is not just a sketch, this is an accurate diagram that you have to draw, and you're also not given a grid, so you have to be careful that you are as accurate as you can be. Okay, now over here, because two boxes represent 1 unit, so I'm going to make sure that there are only two boxes which are covered. Okay, all right, so we can see that from the center, this is 1 unit, so that is the radius. From the center, that is 1 unit, that is the radius. Down, it's 1 unit, and up, it's 1 unit. So let me just extend a little bit. All right. Okay, so that is the circle, okay, from the first inequality which was given to us. Now, the second inequality is that the argument of z, so basically angle of z from 1, 0. Where is 1, 0? It's over here. This is 1, 0. Okay, now I'm going to draw a straight line. So basically, when the question comes down to this one, the argument, right? So here you have to understand that this is your temporary axis. So your x-axis and your y-axis basically start from here. Okay, now you need to draw a straight line from here, and the angle should be less than or equal to 3 over 4 pi. Now 3 over 4 pi is 3/4 of pi, right? So if I were to do it in easy words, okay, so 3/4 of a pi, that means in terms of degrees that would be 3 upon 4 multiplied by 180, so that would give us 135 degrees. Now 135 degrees basically comes in this region, right, over here, and it would, because you know that this is 0 and this is 90, so 90 is actually pi upon 2, then this is pi, which is 180 degrees. Between 90 and 180 degrees over here from the exact center. All right, so let me draw this. It will be at about 45 degrees over here. Okay, now this angle that you have here, that will be 3 over 4 pi. So 3 over 4 pi is actually 135 degrees. Okay, so that will give you a better idea. So it's an obtuse angle. All right, now you need to shade the inequality. Sorry, you have to shade the region. It says shade the region whose points represent complex numbers z satisfying the inequalities. Now we need to shade the region that are satisfied by these given inequalities. So the distance of z, the distance of the complex number, should be less than or equal to 1. That means that your complex number is within the circle. Okay, it lies within the circle. All right, so we know that our region should be inside the circle, but inside the circle there are two parts. We have two segments. This is a minor segment and this is a major segment. So which one are we supposed to shade? Then it says the angle of z. What is z? That is the required complex numbers. Angle of z from 1, 0 should be less than or equal to 3 over 4 pi. If you see that from the beginning of the axis until the line, that is 3 over 4 pi. But what we are interested in is that the angle should be less than or equal to. So therefore, the required region is going to be this part over here. All right, because if I draw an angle from this part, okay, from this part until this part, right? So before I can read this blue line, my angle would be less than 3 over 4 pi. All right, if I go beyond this blue line, then my angle is going to be more than 3 over 4 pi. So that does not satisfy the given inequality. All right, so this is the Argand diagram that you are supposed to draw. Now you're not required to give this temporary axis. Okay, so you can just erase this part. All right, so Yeah, that's pretty much about it. You can if you want, you can draw this line, and then you can show this angle over here. All right, make sure that your axes are clearly labeled. Okay, you are showing that this is the imaginary part, this is the real part, and do not forget to write I, because sometimes what students do is that they forget to write down I. Okay. So that is the end of question number 2. All right, question number 3. The variables x and y satisfy the equation x is equal to a times 3 to the power minus I, where a is a constant. Explain why the graph of y against ln x is a straight line, and state the exact value of the gradient of the line. Okay, so before we can prove that y the graph of y against ln x is a straight line, first we have to rearrange the equation in the form y equals mx plus c. Okay, then only we can justify this statement. Now, because your graph is going to be y against ln x, that means that this is going to be in the form m times ln x plus c. Okay, all right. So first let us write down the original equation. X is equal to a times 3 to the power minus y. Okay, now we're going to take ln both sides. So this becomes ln x equals ln a 3 to the power minus y. Ln x equals, now what we can do is, by using the laws of logarithm, we can separate these two. So this becomes ln a plus ln 3 to the power minus y. Okay, then minus y, again using the power law of logarithms, we can multiply minus y on this side. So this becomes ln a minus y times ln 3. Now, definitely, because I want my variable to be positive, right? Because I want to make y the subject and I want my y to be positive. So I'm going to shift y minus y ln 3 on that side, and ln x will come onto this side. So this becomes y ln 3 equals minus ln x plus ln a. Now I'm going to divide both sides by ln 3. So I will be left with minus 1 upon ln 3 times ln x plus ln a over ln 3. So you can see that now this equation has been rearranged in the form y equals mx plus c. So therefore your gradient is going to be minus 1 over ln 3, and your y-intercept will be ln a upon ln 3. But here we have to explain, okay, because it is asking you to explain, that means that statements are required. You have to explain in wordings. Okay, now what can we say, or how do we have to justify this? So we can say that the equation can be in the form, we can say can be written in the form y equals mx plus c, which is linear, or you can say straight line equation. Okay, so this is how we have justified that y the graph of y against ln x is a straight line. Then it also asks you to state the exact value of the gradient of the line. Okay, so we can say gradient, therefore gradient is equal to minus 1 upon ln 3. All right. Okay, so let's move to part B. It is given that the line intersects the y-axis at the point where y equals to 1.3. So if it is intersecting the y-axis, that means at y-axis x is equal to 0. So the coordinate which is given to us is 0, comma 1.3. Calculate the value of a, giving your answer correct to 2 decimal places. Okay, what was a? A was part of y-intercept. Okay, so they have given you the y-intercept, right? So all you have to do is you have to equate ln a upon ln 3 to c. So first of all, I'm going to say that C is equal to 1.3. Okay, or let me just write it as a whole, because C, we also have constant of integration, right? So we can say y-intercept equals 1.3. So from the equation, we know that C is equal to ln A over ln 3. Okay, so now all I have to do is I have to put these values into the equation. So C is 1.3 ln A upon ln 3. So we have 1.3 ln 3 equals to ln A. Now ln A, okay, let me write it again. Ln A is equal to 1.3 ln 3. Now ln A basically means log to the base of E, log to the base E of A equals to 1.3 ln 3. So that means that I can write A is equal to E to the power 1.3 ln 3. Okay, so this is the exact value. So if the question asks you to give your to leave your answer in the exact form, then we'll just leave our answer in this way. But since the question asks you to give your answer to do into two decimal places, so therefore I'm going to write A is equal to, let me calculate the value, E to the power 1.3 ln 3. So that gives us 4.1711. So we can just write 4.17, and that is your answer to this equation, to this question. All right, question number 4. Using integration by parts, find the exact value of the integral of tan inverse half x with respect to x between the limits to 0. Okay. All right. Now, if you look at this equation, okay, first of all, we need to understand where exactly do we apply integration by parts. So we apply integration by parts in those questions or in those situations where we have a product of two functions being integrated. Okay, so if I have a function of x, so let's say this is x1 multiplied by x2, which is another function of x, and I integrate this with respect to x. So this is where I have to apply integration by parts. If you look over here, tan inverse of half x, this is one single function. So how can I apply integration by parts? I just have to modify the question a little bit so that I am able to use this technique. What I can do here is I can say that we have 1 times tan inverse 1 upon 2x with respect to x. Okay, now here we have two different functions. Okay, so we have to choose u, okay, and we have to choose v dash, right? Now what I've taught you earlier is that we can use light. Okay, we can use this abbreviation, this or these initials, to remember that what should we choose for u. L stands for ln. Okay, I is the inverse of trig function, which is this one. Okay, so you can see that this comes first. Okay, then one will fall under this category of algebra. So algebra comes later, so that means we have to uh, choose from this sequence, right? So therefore tan inverse has a higher priority, so we're going to write it over here, and v dash will be 1. Now I'm going to write u dash. Okay, so u dash is going to be 1 over 1 plus half x whole square multiplied by the derivative of what's inside the function. So that will be 1 upon 2. Okay, and v will be just x. Now how do I know this one? Now you need to know this from the standard results, that if you differentiate tan inverse of x, so you basically get 1 plus 1 over 1 plus x square. So this is the standard result. But if I want to differentiate tan inverse of ax, okay, where a is a constant. So the answer to this will be 1 over 1 plus ax whole square multiplied by the derivative of what's inside the function, which is a. So you can see that this is exactly what I've done here. All right, so ax that comes underneath whole squared multiplied by the derivative of what's inside the function, which is half. So if I simplify this, so I'm going to get 1 over 2 times 1 plus 1 upon 4 x square, okay, and then I can rearrange it and we can write it as 1 over 2 plus half x square. Okay, so we can expand this bracket and this is what we'll get. All right, so the formula for integration by parts is u v dash is equal to, so this is the question, right? So this was your u and this is your v dash. So that is equal to uv minus the integral of vu dash. Okay, some of you might know this in this manner: uv minus the integral of v du dx. Okay, and this part can be written as u dv dx times dx and the integral of this. So there are two notations. You can use any notation for your convenience. All right, so uv will be tan inverse of half x multiplied by x. Okay, so we can say x times tan inverse of half x minus the integral of vu dash. So that is x multiplied by this entire uh, this whole thing, right? So that will be x times 1 over 2 plus 1 over 2 x square dx. All right. Okay. If I multiply this x inside, okay, so if let's say that I just straight away write it inside over here, so what we can notice is that this integral is in the form f dash x over f of x, right? Because if I try to differentiate the denominator, so this 2 will become 0 and this becomes 2 times half x. So that will be 2 and 2 cancel. So you'll be just left with x. Isn't that x the derivative of this already given over here? So you have a derivative of a function divided by the original function. So when this situation pops up, we can directly write this as, so we can say that this becomes ln 2 plus half x square, okay, and then we're going to write the limits on this side. All right, now all we have to do is we just need to plug in the values. So the first limit is 2, so 2 tan inverse of half into 2 minus ln 2 plus 1 over 2 2 square. So that is my first bracket. The second one, if this is 0, x is 0, right? So everything, the first whole term becomes 0. And on this side, we have minus ln 2 plus 0. Because here, if I plug in the value of 0, so this whole term becomes 0. All right. Then this becomes, okay, half times 2. So 2 and 2 cancel. So tan inverse of 1. Tan inverse of 1 is pi upon 4 minus ln half times 2 square, that is 4. 4 divided by 2, that is 2. 2 plus 2, 4. So that will be ln 4 plus ln 2. Minus minus plus, so you get ln 2. All right. So this becomes pi upon 2 minus ln. Okay, what we can do here is, if we write it in this form, so I can combine them into one single fraction, into one single logarithm. That will be 2 over 4. Okay, and that gives us pi upon 2 plus ln 1 over 2. Okay, so that's your answer. Now there is another way that you can represent this answer. That is, I can say that pi over 2 plus ln 2 to the power minus 1. Okay, because 2 is at the denominator, you take it up, and then this minus multiplies over here, so you have pi over 2 minus ln 2. So that is another way to represent your answer. Both of them are exactly the same and both of them are correct. All right, so let's move to question number 5 now. The complex number u is given by u is equal to 10 minus 4 root 6I. Find the two square roots of u, giving your answers in the form a plus ib, where a and b are real and exact. Okay, so we know that u is equal to 10 minus 4 root 6I. We need to find a square root of this complex number. Okay, so basically we know that a square root of a complex number is also a complex number. Okay, so when we take a square root of a complex number, the resulting answer will also be a complex number. So if I take square root of 10 minus 4 root 6I, then my answer will be in the form a plus bi. Okay, so this will be a complex number. We don't know what is a, we don't know what is b. If I square both sides, so we can get rid of the square root, and a plus bi will be squared. So if I expand this, so this becomes a square plus abi plus again abi plus b square I square. Okay, so this becomes a square. All right, and this will be 2abi. Now we know that I square has a value of minus 1. Okay, so we are going to substitute that minus 1 over here. So we have b squared times minus 1. Now because we knew that I squared is minus 1, right? So now this term also becomes part of the real part. So we can write the real parts in one place, and then this is the imaginary part. So let me write this down: 10 minus 4 root 6 I. Now what we can do now is that we can compare the real parts with each other, and we can compare the imaginary parts with each other, and this way we will be able to obtain two equations that we can solve simultaneously. So comparing or compare the real parts, that gives us 10 equals a square minus b square. Okay, the imaginary part contains the I, right? Remember that. So this is how we can differentiate the what is the real part and what is the imaginary part. All right, so this is my equation 1. Then compare the imaginary parts. So that will be minus 4 root 6. Now remember, we are comparing the imaginary part. Okay, so we are not going to write I. Just like how we say that compare the coefficient of x squared in the binomial expansion. So we only write the value of the coefficient. We do not write the x squared itself when we are comparing them. So similarly, we are not going to write I over here. So I'm just going to write minus 4 root 6 is equal to 2ab. Now, what I can do is I can make any one of them the subject of the formula. So let's say that I make b the subject of the formula. So b is equal to minus 4 root 6 divided by 2a. That would give us minus 2 root 6 over a. Okay, and that is my second equation. All right, now what I'm going to do is I'm going to substitute 2 in 1. So because now I've made b the subject, I'm going to substitute this equation into the first one. So 10 is equal to a square minus minus 2 root 6 over a whole square. Okay, that will be 10 equals a squared minus, so minus 2 root 6. That would basically mean the square of minus 2 will be 4. So you have 4 times, and root 6 whole square, that would mean 6 upon a square. Okay, so that would mean 10 equals a square minus 24 upon a square. Now I can multiply both sides by a square. So that would give us 10a square equals a to the power of 4 minus 24. Rearrange this equation and you will end up with a disguised quadratic equation. Okay, so I need to find the factors of 24 in a way that when I add them, I should get minus 10. So we can see that that will be minus 12 plus 2. Sorry, this is minus. So now I can take a square common. So a square minus 12 plus 2 will be common. So again, a square minus 12 equals to 0. A square minus 12 times a square plus 2 equals to 0. A square equals to 12 and a square equals to minus 2. Now look, you have to be very clear on what the question says. Okay, even when you're working, okay, you have to go back to the question to see what's given. It said that a and b are real, okay, and they're exact. So if I were to work this out, okay, that would end up as square root of minus 2, right? So that would be that would give me a complex number, but a is not a complex value, therefore we will reject this solution, and we will only proceed with this solution. So here we know that a square is equal to 12. That means a is equal to plus minus square root of 12. And if I simplify it, I would get plus minus 2 root 3. Okay, so now we have found two values of a. So when a is equal to 2 root 3, what is the value of b? From the second equation, now we just plug in the value. So minus 2 root 6 over 2 root 3. So 2 and 2 will cancel, and minus root 6 over over root 3. So that would give us minus root 2. All right. And when you plug in the value, a equals to minus 2 root 3. So b is equal to minus 2 root 6 over minus 2 root 3. So minus minus will cancel out and you would get root 2. Okay. All right. So therefore, square roots of u are 2 root 3, that is the first x value, minus I root 2, and the second will be minus 2 root 3 plus I root 2. So that's your solution to this question. All right. So let's move to question number 6 now. Question number 6 is, prove that cosec 2 theta minus cot 2 theta is equivalent to tan theta. Okay. All right. Now look, because you need to get your answer in tan theta, right? So what I can imagine is that the last step that would give me this solution would be that I should end up with sine theta over cos theta. Somehow, after doing my working, I should end up with sine theta over cos theta, and that in turn I'm going to write down as tan theta. Okay, all right. Why is it important? Because it just gives you an idea of what your required steps would be. So now this gives me an idea that I should somehow end up with sine theta and cos theta. Okay, all right. So cosec 2 theta, let me write this down first. minus cot 2 theta. So this is equivalent to 1 over sine 2 theta minus cos 2 theta over sine 2 theta. Okay, all right. Now you see why I wrote this, because I could have written minus 1 upon tan theta, right? But we're not interested in tan theta directly, because we cannot get tan theta directly, right? So that's why I chose to write that down as cos 2 theta over sine 2 theta, which is the same thing as 1 over tan 2 theta, because even if you would have written that, you would have to express this further into some other form, and this is the other form that we can express this into. All right, so we can see that sine 2 theta we have same on the both sides, so we can combine them in one single fraction, sine 2 theta, and on the numerator we have 1 minus cos 2 theta. Now cos theta, there are three double angle formula for cos 2 theta. Okay, so we have cos squared theta minus sine squared theta, we have 2 cos squared theta minus 1, and we have 1 minus 2 sine squared theta. Now how am I supposed to know that which one is applicable in this case? Okay, now remember what we did earlier. We need to end up with sine 2 theta at the top, and we need to end up with cos theta at the bottom, right? So in this case, I'm going to use this one. All right, because if I because I don't want anything else at the in the numerator. I only want sine somehow. So the only one that gives me sine is this double angle formula. So this one will be written as 1 minus 2 sine squared theta, whereas in the denominator we need to have cos 2 theta, right? So sine 2 theta only has one double angle formula, which is 2 sine theta cos theta. All right, okay, if I simplify this, so we get 1 minus 1 plus 2 sine squared theta over 2 sine theta cos theta. 1 minus 1 will cancel out. We'll be left with 2 sine squared theta over 2 sine theta cos theta. Okay, one of these sine thetas will cancel, the 2's will cancel, and you will be left with sine theta over cos theta, and that would be equivalent to tan theta. And that's your answer. Okay, all right. Part B. Hence, show that the integral of cosec 2 theta minus cot 2 theta with respect to theta between the limits pi over 3 and pi over 4 is equal to half ln 2. Now, first I'm going to compare, is this exactly the same that we proved earlier? So, yes, this is exactly the same. So that means that instead of this whole expression, I can just write down tan theta. So I'm going to write down pi over 3, pi over 4, tan theta d theta. So we have to integrate tan theta with respect to theta. Now, before you can integrate this, okay, you need to express this in a form that is possible to integrate, because we do not have a standard result of tan theta being integrated. Okay, so what we're going to do is, we know that tan theta is sine theta over cos theta. Okay, now you can notice that this is in the form f dash x over f of x, except that that we have to make some minor adjustments here. Our original function is cos theta. The derivative of cos theta is minus sine theta, but we do not have a minus over here, so we have to put the minus in order to bring into this form. So what I'm going to do here is pi over 3, pi over 4 sine theta over cos theta. Now I'm going to put a minus sign over here and a minus sign outside, so balance it out. Okay, and we have d theta. Now you can see that this is exactly in the form f dash x over f of x. So therefore I can integrate this, and we have minus ln cos theta and the limits will be pi over 3 pi upon 4. Now you can see that there's a negative ln inside, right? If I want to get rid of this negative, I can swap the limits. So what we can do is, this is equivalent to ln cos theta with the limits being swapped. So at the top now I have pi upon 4, and at the bottom I have pi upon 3. Okay, all right. Now definitely the answer is going to be the same, right? So that goes without saying. So now we have ln cos pi upon 4 minus ln cos pi upon 3. Okay, all right. So if I work this out, cos pi upon 4 will give us ln root 2 upon 2 minus ln half. Okay, pi upon 3, that'll be half cos pi upon 3. Okay, so using the laws of logarithm, I can combine them into one fraction. So this will be ln 2 upon 2 divided by 1 upon 2. Okay, that would give me, so 2 and 2 will cancel, so we'll get ln root 2. This is actually ln 2 to the power of half, and then I can take the power over here, so we have half ln 2, and this is the exact form that was given in the question. All right, question number 7. A curve is such that the gradient at a general point with coordinates xy is proportional to y upon root x plus 1. The curve passes through the points with coordinates 0, 1 and 3e. Okay, so this is the initial condition and this is a boundary condition that we have. By setting up and solving a differential equation, find the equation of the curve expressing y in terms of x. Okay, so it says that the gradient at a general point, gradient is represented by dy dx, okay, is proportional to y upon root x plus 1. So first of all, I'm going to write down that dy dx is proportional to y upon root x plus 1. So this can be written in the form of equation as dy dx equals k times, or you can just write it along with y. So k y over root x plus 1. This is the differential equation that we have set up. Now, by separating the variables, we can bring out y onto the left hand side. So I have 1 upon y dy dx equals k times x plus 1 to the power minus half. Okay, now I can separate the variables. So that will be, we have separated the variables. Now we can integrate. So I can integrate this with respect to y, and I can integrate this part where k is a constant, so I can just write it outside the integral sign. So x plus 1 to the power minus half dx. Okay, so on the left hand side, the integral of 1 upon y, that is ln y, equals k times, so this will be, you add 1 to the power, so that becomes x plus 1 to the power of half divided by the new power, which is 1 upon 2, and multiply by the derivative of what's inside the function, so that is just 1, right, plus the constant of integration, because you can see that we do not have any limits, right? This is indefinite integral, so that means that we have to write plus c. Okay, so if I rearrange this, I would get ln y equals 2k x plus 1 to the power half plus c. All right, now what we can do here is that we can write this in a different form. Ln y is basically log to the base e of y, right? So I can say that y is equal to e to the power 2k times x plus 1 to the power of half plus c. All right, now this part can be further separated. We can say 2k And over here, x plus 1 to the power half, I can just write it as square root of x plus 1 times e to the power of c. Because look, from the laws of indices, we know that a to the power m times a to the power n means a to the power m plus n. So this was in this form, a to the power m plus n, and I've split it and written in this form. Okay, so this is something that you have studied it back in O-level maths or IGCSE maths, the rules of indices. So now this will actually equal to this e to the power c is now a constant. It is a new constant. So this constant I'm going to represent with a. And then I have a times e to the power 2k root x plus 1. Now this is my differential equation. So I have already set it up. You see, the question was telling you to express y in terms of x. I have expressed y in terms of x. Now all I have to do now is to find the value of a and the value of k, and that's it. My job is done. Okay. All right. So let's use the first value, which was 0, 1. So at 0, 1, y y is 1. So 1 is equal to a times e to the power 2k root of 0 plus 1. So 0 plus 1 is 1, root of 1 is also 1. So your equation is 1 equals a times e to the power 2k. Okay, so that means I can rearrange it and I can say that a is equal to 1 over e to the power 2k. That is my first equation. Okay. All right. The second condition that's given to us is 3 comma e. So at 3 comma e is equal to a times e to the power 2k. Okay, and that will be square root of x plus 1. So that will be 3 plus 1. So you have I'll write it here. E is equal to a times e to the power 3 plus 1. That will be 4, and root of 4 is 2. So that means this becomes e to the power 4k. All right, and yeah, we cannot solve it any further, so that's our equation number 2. Now I can substitute 1 in 2. So that will be e is equal to 1 over e to the power 2k time, that is your a, times e to the power 4k. All right, so this will basically be, sorry, this k is actually in the power. Okay, so that will be just like saying that e to the power divided by e to the power 2k. The bases are the same, so the powers are going to subtract. So 4k minus 2k, that will be e to the power 2k. So we can say that e is equal to e to the power 2k. All right, so because our bases are the same, okay, the power will also be equal. This will be 1 is equal to 2k, and therefore k will be equal to half. This rule is just similar to, let's say I have x to the power of a equals to x to the power of 3. So because my bases are the same, that means the powers will also be equal. So therefore I can say a is equal to 3. So this is something which is similar to this one. All right, so we found our first constant. Now I can just plug in this value back in equation 1. So a is equal to 1 upon e to the power 2k. So that is 1 upon e to the power 2 times half. So 2 and 2 will cancel. You will be left with 1 upon e. So you can just write 1 upon e, or you can say e to the power minus 1. That's up to you. Therefore, our equation is going to be, all right, a is 1 upon e. Then we have this equation here. So e to the power 2k root x plus 1. So we're going to write down e to the power 2k. So k was half root x plus 1. Okay, so 2 times half, that will cancel. So you're going to get e to the power minus 1 times e to the power x plus 1 under root. Okay, and therefore we can write this in one simple form. We can add the powers. So I'll be left with root x plus 1 minus 1. Okay, and that is your final answer. Because look, the thing is that we have to rearrange it. All right, we have to rearrange it because the value of a was in terms of e. Okay, if it would have been just some any other constant, right? So let's say if I would have got 1 upon 5, for example. So after plugging in the values, okay, I would have left it over here. But because it is in terms of e and we have e over here as well as the base, so I have to simplify it further. Okay, so that is the final answer to this part of the question. All right, so let's move to the next question. Question number 8. The equation of a curve is y equals to e to the power minus 5x tan squared x for x between minus pi upon 2 and pi upon 2 radians. Find the x coordinates of the stationary points of the curve. Okay. It says stationary points, right? It's plural. That means that we are going to find more than one stationary point. Give your answers correct to 3 decimal places where appropriate. All right. Now, we know that at stationary point dy dx is equal to 0. So that means first we need to find what is dy dx, what is our gradient function. So let me write this down first. Y equals to e to the power minus 5x times tan squared x. So since this is a product of two functions and we have to differentiate it, so we will be using the product rule. So u is equal to e to the power minus 5x, v is equal to tan squared x. So we can write this as tan x to the power 2. Okay, u dash will be, first I'm going to write e to the power minus 5x multiplied by the derivative of what's inside the function. So that will be minus 5. And v dash is going to be, so here simply we have to use the chain rule. So 2 times tan x multiply by the derivative of what's inside the function, which is tan x. The derivative of tan x is sec square x. Okay, so therefore this becomes 2 tan x sec squared x. Okay. Now we know that dy dx is vu dash plus uv dash. So therefore vu dash, that will be minus 5 e to the power minus 5x times tan squared x, minus 5 e to the power minus 5x times tan squared x plus then uv dash. So that will be e to the power minus 5x times 2 tan x sec squared x. Okay. Now remember one thing, whenever you need to find divide dx and whenever you have to equate it to 0, you must express this part as in a factorized form. Okay, and I'll tell you in a minute that why do we need to do that. So first let us see that what can we take here as common. We can take tan x, okay, and we can take e to the power minus 5x as common. So we'll say tan x times e to the power minus 5x. Okay, that has been taken common. So here we will be left with minus 5 tan x plus 2 sec squared x. Okay, all right. Now that we have expressed this in factorized form, now we can say that at stationary points, dy dx is equal to 0. So we can say that 0 equals tan x e to the power minus 5x and 2 sec squared x minus 5 tan x, right? So I've just I just wrote this in the first place. Now when we have a factorized form, so for example, when we end up with something like this, x times x minus 1 equals to 0. So what do? We say that either x is equal to 0 or x minus 1 is equal to 0. So the same concept applies here. So we're going to say that either 10x is equal to 0 or e to the power minus x is equal to 0 or 2 sec squared x minus 5 10x is equal to 0. Okay, all right. Now when we say 10x is equal to 0, so this is something that we have to know the graph of. Okay, so we can solve this, or we can find the solutions to this equation if we know the graph. Okay, so the graph of 10x is something like this. Then it goes up. Then you have asymptotes at 90 degrees, so that will be pi upon 2. And you have asymptote over here at minus 90 degrees, so that is minus pi upon 2. So here you can see that x is equal to 0, right? So where does 10x becomes 0? When x is equal to 0. So therefore we know that 10x is equal to 0. So therefore we can say that x is equal to 0. So that is our first x coordinate of a stationary point. Okay, all right. Coming to the second one, now because we are limited between this range, right? This is the range, right? That is given in the question, minus pi upon 2 and pi upon 2. So we cannot go further in the graph. Coming to this point, okay, e to the power minus 5x is equal to 0. This equation has no solution because for no value of x can you find a value of y which is 0. Okay. Now coming to this part, now there are two methods that you can use over here. I'm going to use one method, and by the end of it, I'll tell you another method as well. The first method is that you can write both of them in terms of sine and cos. So 2 sec squared x will be 2 upon cos squared x, and this becomes 5 sine x upon 10x. Sorry, 5 sine x upon cos x equals to 0. Then we can shift this entire expression on the other side. So this becomes 2 over cos squared x equals 5 sine x over cos x. Okay. Then I can multiply both sides by cos squared x. So I'll end up with, so when this cos squared x multiplies, one of the cos x will cancel. So we will be left with 5 sine x cos x. Okay. Now we know that sine 2x is equal to 2 sine x cos x, right? So that means if I make sine x cos x the subject of the formula, I'll end up with half sine 2x. Now this part I can replace over here. I can substitute over here. So I'll end up with 2 equals 5 times 1 upon 2 sine 2x. Okay. All right. Now after this, we can make sine 2x the subject of the formula. So 2 goes on the other side, 5 will be divided, so that will be 4 upon 5. 2x is equal to sine inverse of 4 upon 5. Make sure that your calculator is in radians. So that will give us 2x is equal to 0.9273. Okay. Now the given range is that x is between minus pi upon 2 and pi upon 2. The new range, because we have to modify the range, right? So we have to modify the range for 2x. So that will be minus pi till pi. Now here we can use the ASTC diagram, or some of you might be aware of it as cast diagram. Okay, so we have A, S, T, C. Now we know that our sine 2x, okay, our sine ratio is positive. So sine is positive in the first quadrant and in the second quadrant. So the first solution will be over here and the second solution is going to be over here. Okay. Now, the second solution will be 2x is equal to, now this one is 0.9273, right? So what we can do here is that we know that the principal solution is 0.9273. So this will be pi minus 0.9273. Okay, and that will give us 2.214 radians. Okay, so now from this part we have two equations, sorry, we have two solutions. We know that 2x is equal to 0.9273 and 2.214. So we can divide both sides. So we'll get 0.464 and 1.107 radians. Therefore, now do not forget that we found another solution that was x is equal to 0. Okay, so that means our total solutions will be x is equal to 0, x is equal to 0.464 and 1.107 radians. Okay, make sure that you also keep in mind that your answer is supposed to be to 3 decimal places. Okay, now generally we either write our answers in 3SF. Okay, that's the general rule of thumb, but over here the answer was required in up to 3 decimal places. Okay, all right. Now the second method that I was talking about is that starting from this point, okay, here the method that I used was using cos squared x and sin x and cos x, right? So doing them in terms of sin x and cos x. So there's another method. Let me first write this down. So we have 2 sec squared x equals to 5 tan x, right? Now we know the identity that 1 plus tan squared x is equivalent to sec squared x. So you can substitute 1 plus tan squared x, okay, equals to 5 tan x. Then we have 2 plus 2 tan squared x minus 5 tan x equals to 0. We can rearrange this. And you can see that this is a quadratic equation. So now what you can do is you can solve this quadratic equation and you'll get two solutions from here as well. Okay, so that is the end of question number 8. All right, so let's move to the next question. Question number 9. Let f of x equals 14 minus 3x plus 2x squared divided by 2 plus x times 3 plus x squared. Express f of x in partial fractions. Okay, so what we can notice here is that this is a linear factor and then this is a quadratic factor. Okay, so we can write the numerator as it is, divided by 2 plus x times 3 plus x squared. So this is equivalent to, now for a linear factor we will write a upon 2 plus x and for a quadratic factor the numerator should be 1 degree less than the denominator. So if the denominator is a quadratic factor, that means that my numerator will be a linear number. Okay, or not, it will be in a linear form. So that will be bx plus c. Okay, now we will multiply both sides by 2 plus x times 3 plus x squared. So this whole expression will multiply both sides. So from here it will be cancelled, and over here 2 plus x will cancel with this, and here we will have 3 plus x square, and on this side 3 plus x square will be cancelled and 2 plus x will remain. Okay, now we need to find the coefficients. We need to find a, b, and c. So we need to find these values. Now what we can do is we can say that let x is equal to -2. Okay, why -2? Because I need to cancel out some of the terms, and there should be only one unknown left in the equation. Okay, so we can say 14 minus 3 times -2 plus 2 times -2 whole square equals 8 times 3 plus -2 whole square plus, now you can see that this whole term, okay, will become 0. Okay, because 2 minus 2, that will be equal to 0, and that was deliberate, right? That is exactly what we wanted. So now we will simplify this. So here we have 14 minus 3 minus 2, that will be plus 6. So 14 plus 6 is 20, and 2 square, that is 4. 4 times 2 is 8. 8 plus 20, so that should give us 28. Okay, then here we have 3 plus 4, so that should be 7a. So therefore the value of a will be 28 divided by 7, which is equal to 4. All right, so that's my first constant. Now we can say that let x is equal to 0, because when I say x equals to 0, b will cancel out. Okay, a I already found out, and now I can find c. So here we'll be left with just 14 equals a times 3 plus 0 plus, okay, b will cancel, plus c times 2 plus 0. Now the value of a is 4. So 4 times 3 plus, here we have c plus 0, that is 0, and 2 plus 0, that is 2. So 2 times c will be 2c. So 4 times 3 is 12. So we can say 14 minus 12, okay, and divide by 2. That is equal to c. So therefore c is equal to 1. Now in order to find b, we can compare the coefficient of b of x square. Compare the coefficient of x square, because now there is no value of x for which I can cancel other numbers and find b. Yes, there is another way. You can just use, you can just say let x is equal to 1. Okay, so when you substitute 1 into the equation for every x value, and you already found a and c, so you can now find b, but that is a longer working. Okay, so if you are comfortable with that method, that is perfectly fine. Okay, I personally like this method because it is much more simpler, and you can see that how is it simpler. The coefficient of x square on the left hand side is 2, so I'm going to write 2 equals the coefficient of x square. So one of the coefficient I'm going to get is when a multiply with x square. So from here, one of the coefficient of x square is a, and from here, when this bx multiplies this x, so that becomes bx square. So the second coefficient will be b. All right, we already know the value of a, that was 4. So therefore b is equal to 2 minus 4, which is -2. Okay, so therefore f of x can now be expressed as partial fractions. So we have a upon 2 plus x, so that will be 4 upon 2 plus x, plus we have bx plus c, so that will be minus 2x plus c, c is 1, upon 3 plus x square. Okay, now in order to avoid the confusion with plus or minus, okay, it's better that you write it in this form: 2 plus x plus 1 minus 2x over 3 plus x square. You can just write 1 over here, and now that confusion is gone. So this is our answer to part A. All right, part B. Hence, obtain the expansion of f of x in ascending powers of x up to and including the term in x square. Okay, so first let me write this down. So f of x is 4 upon 2 plus x, but now I'm going to write it in this form: 2 plus x to the power minus 1 plus 1 minus 2x times 3 plus x square. So 1 minus 2x times 3 plus x squared to the power of minus 1. Okay, now let us first separately work out the expansion of this and the expansion of this. Okay, so 2 plus x to the power of minus 1. Now you can see that the binomial expansion formula that we use is 1 plus x to the power n is equal to 1 plus nx plus n times n minus 1 over 2 factorial x square plus n times n minus 1 times n minus 2 over 3 factorial x cubed. Okay, now because we're only interested in this part, so I'm just going to limit my formula to this portion. Okay, now here we can see that in order to be able to use this formula, your binomial term should be in this form, your expression should be in this form, but it is not in this form. Okay, this one should be 1, so I have to make this 1. So what I'm going to do is I'm going to factorize 2 outside. So when I factorize 2 outside, this becomes 1 plus x upon 2. Okay, and then I put back the bracket with minus 1 to the power minus 1. Now if I open up the bracket, so I get 2 to the power minus 1 times 1 plus x upon 2 to the power minus 1. 2 to the power minus 1 is 1 upon 2 times 1 plus x upon 2 to the power minus 1. Now I can just write 1 upon 2 on the outside, and I'm just going to proceed with the normal expansion. So we have 1 plus nx, so that will be 1 plus n is the power, which is minus 1, and x is going to be this entire term, plus n times n minus 1, so that will be minus 2 over 2 factorial x square, so x upon 2 whole square, bracket closed. 1 upon 2 times 1 minus, or maybe we can write it in this form, 1 minus half x plus, now minus 1 minus 2, that is 2, and 2 factorial is also 2, so this will cancel out. Then we are left with 1 upon 4 x square. Finally, if I expand this, I'm going to get, it's hanging for a bit, let me fix it. Okay, so we have 1 upon 2 minus 1 upon 4x plus 1 upon 8x square. So this is the expansion for this part. Okay, now we're going to proceed with 3 plus x square to the power minus 1. Okay, all right, so what we can do here is 3 plus x square to the power minus 1. Again, we have to factorize this. So this will be 3 times 1 plus x square upon 3, and then you put back the bracket with minus 1. So this will be 3 to the power minus 1 times 1 plus x square upon 3 to the power minus 1. So 3 to the power minus 1 is 1 upon 3, and this will be 1 plus x square over 3 to the power minus 1, and now we can expand it. So this will be 1 plus nx, n is minus 1, and x is going to be x square over 3. Now remember, the question told you to expand until and including the term x square, so we don't have to go further. All right, so we can just stop here, simplify it. So 1 upon 3 times 1, that is 1 upon 3. Here it becomes minus x square over 3. So 1 over 3 times minus x square over 3 will be 1 over 9x square. Okay. All right. Now that we have worked out the expansion, so let's write f of x again. So this time is going to be 4 times the expansion of what we found here. So that will be 4 times 1 over 2 minus 1 over 4x plus 1 over 8x square. After that, we had plus 1 minus 2x times this part, right? So the expansion for this part is 1 over 3 minus 1 over 9x square. So let's open up the bracket. 4 times half will be 2. 4 times minus 1 upon 4. So 4 and 4 cancels. We'll be left with x. 4 times 1 upon 8x square will be half x square. Then over here, so you can see that here, if I multiply minus 2x with minus 1 upon 9x square, right? So it will give us x cubed, but we don't need x cubed. Okay, so we are not going to do that. We'll just multiply 1 by 1 upon 3, so that is 1 upon 3. 1 times minus 1 over 9x square. Okay, then minus 2x times 1 upon 3, that will be minus 2 upon 3x. Okay, and that's it. So I'm not going to do the fourth term. Now collecting like terms, so half x square minus 1 upon 9. Okay, so we have half x square minus 1 upon 9x square. Let me work this out. So that will give us, let me write it here, 7 over 18x square. Then we have minus x minus 2 over 3. So minus 1 minus 2 over 3, that gives us minus 5 upon 3x. And here we add the constants. So 2 plus 1 over 3, that gives us 7 upon 3. Okay, so that is the answer to question number 9, part B. Okay, question number 10. The diagram shows a trapezium ABCD in which AD is equal to BC equals to R. Okay, this is AD and this is R and this is BC and this is R. Okay, and AB is equal to 2R. Okay, this is AB. All right, so that is R plus R, which is 2R. Okay, the acute angles BAD and ABC are both equal to x radians. Okay, so the acute angles BAD, so BAD, this one, and DAB, so that is this one, or ABC rather, this one. Circular arcs of radius R with centers A and B meet at M. Okay, so because you have equal distance on right side and on left side, so M is basically the midpoint, right? And it also mentions over here, it is the midpoint of AB. Given that the sum of the areas of the shaded sectors is 90% of the area of trapezium, show that x satisfies the equation x equals 0.9 times 2 minus cos x sin x. Okay, so if we look at the bigger picture, okay, so let us first translate this statement into an equation. Okay, it says that some of the shaded sectors, okay, what are the sectors? We have sector DAM and we have sector CBM. Okay, or ADM, AMD, whatever you can call it. So we can say that area of sector ADM plus area of sector CBM, right? Or BMC. So the sum of the shaded sectors is means equal to 90%, right? So 90% is actually 0.9 multiplied by the area of trapezium ABCD. So now, if let's say that you are unsure of how you should start the question, so this is how you should start. Try to now fill in the values or fill in the formulas, okay, so that you are able to see clearly what is the missing piece of information. So here we can say that area of sector is half r squared theta, right? So in this case, it is x plus half r squared x, because both of these angles are x, equals 0.9 times. Now we know that the area of trapezium is half into sum of parallel sides multiplied by the perpendicular height between them. So one of these sides will be CD, the second side will be AB, and the height is going to be the distance which is the between the line CD and the point M. Okay, all right. So if I write down this formula, so that will be times half times A plus B times h. Okay, now from here we can see that we do not know what is a and we do not know what is h. So you see, this is how we work out the missing information. And now I know, okay, what is a will be the length of CD, so let's mark this as a. Okay, and we also need to find that if I draw a straight line over here, so that will be your h. Okay, all right. Okay, so we can see that if I draw a straight line over here, so this is a triangle. Now, this R is not the length of this triangle, because R is actually what, BM, right? B to M, that is R. Okay, so okay, if I let's say that this is point X, so I'm talking about triangle BXC. So this is a right angle triangle. Okay, we need to find an expression for H. So this is the opposite side, and we know BC because that is the length, right? So that is the hypotenuse. So opposite upon hypotenuse, we can use sine theta, right? So if I say that, I can write that sine x will be equal to opposite over hypotenuse. So opposite is h and hypotenuse is r, so that will be h upon r. So therefore, if I make h the subject, that will be r sine x. Okay, all right. Similarly, if I find bx, okay, because if you're able to find bx, because look, we need to find a as well, right? For h we are done. Okay, we're just going to replace that back in the original equation. Now I need to find a. One of the ways that we can find a is that we know the total length ab, okay, and a is actually this length. So if I can work out bx, then this length will also be bx because they're identical triangles. Okay, so I can subtract ab minus 2 times bx. That will be equal to a. So ab is the total length. If I find bx and multiply that by 2, so I'll be able to find this length and this length. Subtract both of these lengths from ab, you will be left with this part. That will be a. So that's the main idea. Okay, so AB we already know that that is 2r, that is given in the question. We need to find bx. We can use the same triangle but a different trigonometric ratio. Now I need to find the adjacent, and I have the hypotenuse, so I can use cos theta. So we have cos x equals bx, which is adjacent, over r. Okay, so you can look over here, bx is your adjacent and this r, that is the hypotenuse. So cos theta equals adjacent upon hypotenuse. So again we can rearrange bx and we can write it as r cos x. Okay, so the equation that I just mentioned, that is ab minus 2 times bx, so that will be 2r minus 2r cos x. So that is a. So we have found a in terms of r and x, and we have found h in terms of r and x. So now we can substitute these back into this equation that we worked out in the first place. So let us write this down now. Half r square x. Okay, so this is now I'm gonna continue. Half r square x plus half r square x will give us r square x equals zero point 0.9 times 1 upon 2. Okay, a is 2r minus 2r cos x plus b. Okay, b was 2r because b was ab, right? Then multiply by h. H was r sine x. Okay, all right. So if I am to work this out, hmm, okay, what we can do is there are some cancellations that we can do. So if I see that all of these are multiplied, right? So I can cancel this r from this r. So one of the r's will cancel. Okay, so I'll be left with rx equals 0.9 times 2r plus 2r, that will be 4r. Okay, so we have half times 4r minus 2r cos x times sine x. Okay, now from the inside we can factorize 2, and that 2 will cancel from the half. So I'll have rx equals 0.90 times. Okay, so first I'm going to factorize 2. That 2 will cancel with half, so I will be left with 2r minus r cos x times sine x. Now what I can do is I can take the r common. Okay, r can be taken common too. So rx is equal to 0.90. R has been factorized, so you'll be left with 2 minus cos x sine x. So this r cancels from this r. So I believe that we have reached what the question asked, and yes. So x is equal to, finally we can say x is equal to 0.9 times 2 minus cos x times sine x, and that is the expression which was required. All right, now in part B, it says verify by calculation that x lies between 0.5 and 0.7. Okay, now whenever you have to use this form, okay, so what we can do is the first part is to bring everything on one side, and you should have 0 on the other side. So I'm going to bring this entire expression towards the left. So that will be x minus 0.90 sine x times 2 minus cos x, okay, equals to 0. Now I'm going to say that let f of x equals x minus 0.9 sine x times 2 minus cos x. So basically we have to show that our root lies between 0.5 and 0.7, right? So we can only do that if we rearrange this into this form first, so that we are able to use the sign change rule. So we can justify using the change of sign that yes, our root lies between these 2 points. Okay, so now what I'm going to do is I'm going to say that sorry, now I'm going to directly input the value of 0.5. So f of 0.5 will be 0.5 minus 0.9 sine 0.5 times 2 minus cos 0.5. Okay, so let me work this out. Okay, so if I write this to 3SF, I'll get 0.0157. Okay, all right, let's now plug in the value of 0.7. 0.7 minus 0.90 sine 0.7 times 2 minus cos 0.7. Okay, so now if we plug in this value, okay, so now we get minus 0.0161. So here we can see, okay, let me write it over here, minus 0.0161. All right, so we can see that between 0.5 and 0.7, there has been a sign change. Okay, so that indicates that our root lies between these 2 points. Okay, so we can say since there is a sign change, the root lies between 0.5 and 0.7. Okay, what exactly do we mean by that? Let's just quickly see it over here. So if let's say that this is your x-axis, okay, and there is a curve, okay, the curve goes something like this. Okay, suppose that over here, or in fact it should be the other way around. In this case it should be something like this. Let's just say that it is something like that. So over here, this value, that is 0.5. So for x is equal to 0.5, you have a value which is above the x-axis. So that means that this y value is positive. After passing through this around at 0.7, you can see that over here the y value is negative. So that means that your root lies somewhere between 0.5 and 0.7. We don't know that. Okay, and that is what we are trying to find out. So first, this is how we have verified that, okay, my y value is positive when x is 0.5. So this is how it is. And when I take x as 0.7, the y becomes negative. So that confirms that my root actually lies between these two values. Okay, and you see, this is why the root lies when y is equal to 0. That is why I have rearranged this in the first place. So y has been equated to 0. Okay, and then for what value of x will you have a y that is 0? So that is the root of the equation. Okay, all right. Now it says, show that if a sequence of values in the interval given by the iterative formula converges, then it converges to the root of the equation in part A. Okay, now whenever you have this type of question, okay, so what you should do is first write this but without the ends. Okay, just write it in this form: x is equal to cos inverse 2 minus x upon 0.9 sine x. Okay, now I have to rearrange it, and I have to rearrange and show that after the rearranging part, I'm going to end up with the equation that was given in part A. So what was the equation given in part A? This one. So this is what we have to show. All right. So first of all, this is cos inverse, right? So I'm going to take that to the other side. So this becomes cos x equals 2 minus x over 0.9 sine x. Okay. So what I can do is I can take this entire expression and take that to the other side and take cos x to this side. So this will be x over 0.9 sine x equals 2 minus cos x. Now if you multiply this entire denominator to that side, the entire expression, so that will be 0.9 sine x times 2 minus cos x, right? So we have reached the same equation as in part A, except the sine x is written on the right hand side, so you can just write it in this form. So you can say, therefore x is equal to 0.9 times 2 minus cos x multiplied by sine x. All right, last part of the question. Use this iterative formula to determine x correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Okay, so now they haven't given you the initial value of x, right? So what is the initial value of x that you should use? Because I have to take some value that I can plug into this side and into this side, right? So the ideal value that you can choose is the value which is at the center of these two values. So between 0.5 and 0.7, okay, we have 0.6, right? So 0.6 can be my starting value. So I can say that let x1 is equal to 0.6. Now x2 will be cos inverse of 2 minus x over zero point 0.9 sine x. So x is 0.6 over zero point 0.9 sine 0.6. Okay, so that'll give me the value of, so cos inverse 2 minus 0.6 over 0.9 times sine 0.6. Okay, so I'm going to get 0.6106. Okay, because I have to give the result to 4 decimal places, right? So that is to 4 decimal places. Now what we're going to do is, in your calculator you have an you have a button called the answer key, right? Now instead of substituting this value into this, okay, what you're going to do is cos inverse 2 minus, now what we are going to write is 0.6106, right? But on your calculators what you will be doing is you're just going to write the answer button over here. Well, just write just press the answer key, okay, and then when you press equal sign you will get, let me do that first. Okay, so now I'm going to get 0.6151. All right, now you don't have to substitute anything else. Just press the equal sign one more time, and now that answer button that you substituted here is going to now take this value and plug it into that. So it's going to do the heavy lifting for you. But over here, make sure you show every bit of working, okay, that is required. So 0.6151 over 0.9 times sine 0.6151. So the answer for this is going to be 0.6170. Okay, now if you look closely to 2 decimal places, here I'm getting 0.62 and here I'm getting 0.62 as well. Okay, so this is the indication that I can now stop. So therefore x is equal to 0.62 to 2 decimal places. Now a better way, just to be safe, just to be on safe side, you can just press equal button 2-3 times more just to verify that in the subsequent answers you're still getting 0.62 to 2 decimal places. Okay, so that is the end of our question number 10. All right, so let's continue to question number 11. With respect to the origin O, the points A and B have position vectors given by OA equals to 2i minus j and OB is equal to j minus 2k. Show that OA is equal to OB and use a scalar product to calculate the angle AOB in degrees. Okay. All right, so let us first write down the given vectors. So we have OA, okay, and I prefer doing the calculations in column vector form, okay, because they're easier to deal with, and then in the end we can give our answer in this notation. Okay, if we are asked to give a position vector of any point, so we can give our answer and as the final notation in this form. Okay, but the calculations we can do in the form of column vectors. So OA is 2i minus j, so there is no k component, that means that will be 0. So it will be 2 minus 1 0 and vector OB will be, now there is no I component, so that means I component is 0. J minus 2k, that will be 1 minus 2. Okay. All right. Now we need to use a scalar product. Oh, sorry. First, we need to prove that the lengths of OB and OA and OB are equal. So what we can do is we can calculate the magnitude of OA. So that will be 2 square plus minus 1 square plus 0. So that will be 2 square is 4 and 1 square is 1. So 4 plus 1, that will be 5. So root 5 is the answer. Then the magnitude of vector OB is 0 plus 1 square plus minus 2 whole square under root. And again, we can see we get 1 over here and we get 4 upon over here. So that will be 1 plus 4 root 5. Okay. So we can say therefore OA equals OB. So that is the first part of the question. Now it says use a scalar product to calculate angle AOB in degrees. So if I were to represent it in this form, so let's say that this is point O, this is point A, and this is point B. Okay, so we have the vectors OA and we have the vectors OB. So this is the angle that we need to find. Okay, now the basic formula of scalar product is vector A times vector B equals magnitude of vector A times the magnitude of vector B times cos theta. Okay, so that means theta equals cos inverse of vector A times vector B, okay, over the magnitude of vector A times the magnitude of vector B. So in our case, that will be OA times OB divided by the magnitude of OA and multiplied by the magnitude of OB. Okay, so we already have the magnitude of OA and OB. First, we need to find out what is OA times OB. All right, so let me do that working over here. Vector OA times OB is, so OA was 2 minus 1, 0, and vector OB is 0, 1, minus 2. All right, so that will be 2 times 0 minus 1 times 1 plus 0 times minus 2. Okay, so this becomes 0, this becomes 0, so that will be minus 1. Now I can calculate my theta. So that will be cos inverse of minus 1 upon root 5 times root 5. So that will be cos inverse of minus 1 upon 5. Okay, so therefore angle AOB will be equal to, so let me calculate that. Make sure that your calculator is in degrees mode. So cos inverse of minus 1 divided by 5. So that will be 101.5 degrees. So that is the answer to part 1, part A. Okay, now it says the midpoint of AB is M. Okay, the point P on the line through O and M is such that PA ratio OA is equal to root 7 ratio 1. Okay, so M is the midpoint of AB and P is a line. So P on the line through O and M. Okay, so we have a line O and M. Okay, so let's say that if this is a line and this is O and this is M, so P lies somewhere over here, or it could be over here. So it could be between OM or it could be somewhere here, because we don't know that exactly, right? But if we know that a line that passes through O and M, P is somewhere on that line. Okay, now it says that this point P is such that PA ratio OA is root 7 ratio 1. So a, maybe a is somewhere over here, okay, because a is not lying on this point. So that's what the ratio is given, okay. All right, find the possible position vectors of P. All right, so you can see that this is a 6-mark question, so that means there are multiple steps involved. So let's do our working step by step. First, it mentioned about the midpoint of M. Okay, so first let us calculate that. Now we know that M is the midpoint, right, of AB. Now if I were to write the coordinates of A and B, so that will be 2 minus 1 0, and B would be, what was B? 0 1 minus 2. Okay, 0 1 minus 2. Now we know from coordinate geometry that the formula of calculating a midpoint is x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. Now because there are three coordinates, right, so there are three axes, so therefore this will be z1 plus z2 upon 2. Okay, and you can simply calculate them. So we have 2 plus 0 upon 2, then we have minus 1 plus 1 upon 2, and we have 0 minus 2 upon 2. So that will give us 2 upon 2, that is 1, that will be 0, and that will be minus 1. So we know that the position vector of M will be 1 0 minus 1. Okay, so this is the column vector of OM. All right, so now if we try to work out this ratio, PA ratio OA, okay, so we need to find possible position vectors of P. So basically we need to find OP. So somehow we need to use these vectors. Okay, so let's see how we can use that. This is equal to root 7 ratio 1. Okay, so all right, so we know that the magnitude of OA is root 5, that we calculated this in part A. Okay, so therefore if I want to calculate the magnitude for PA, because we can use the ratio method, right? So let's say that PA ratio OA, that is PA upon OA equals to root 7 upon 1. So if I know the value of OA, I can work out the magnitude of PA. The magnitude of PA will be, so this OA is root 5. You multiply that to the other side, so that becomes root 7 multiplied by root 5. That will give us root 35. Okay, so that is the magnitude of PA. All right. Now you need to realize something, because P lies on this line OM, right? So back in IGCSE or O-level mathematics, you studied about scalar multiples, right? If a line is parallel to another line, then that is a scalar multiple of that line. So what do I mean by that? I can say that, so first let me write this down. Since P lies on OM, okay, so OP is a scalar multiple of OM. Okay, and we can see that if let's say that P lies over here, then that should be a scalar multiple of OM, right? Maybe it's half of OM, maybe it's 1/3 of OM, we don't know that, but it is some scalar multiple, right? So this can be expressed in the form that OP is equal to lambda OM, where lambda is the constant. Okay, all right, so we can say that this is lambda times OM. the coordinates of OM are 1, 0, minus 1. So you can say that this is lambda 0 minus lambda. Okay, so this is the coordinate of OP. Okay, all right. Now from PA, we can write that this is equivalent to OA minus OP. Okay, and we can write down the vector OA was 2 minus 1 0 minus OP is what we found here, lambda 0 minus lambda. So that would give us 2 minus lambda, minus 1 minus 0 is minus 1, 0 minus minus lambda, that is positive lambda. Okay. Now, why did I work this out? If you notice, I have already worked out the magnitude of PA. Sorry about that. I've already worked out the magnitude of PA, right? So now this is these are the coordinates. So this is the column vector that represents PA. If I work out the magnitude of this, so magnitude of PA is equal to 2 minus lambda whole square plus minus 1 whole square plus lambda squared, right? And that will be equal to root 35. Okay, so 2 minus lambda whole square, 2 minus lambda whole square, that will be 4 minus 4 lambda plus lambda square plus 1 plus lambda square equals to root 35. Sorry, my bad. This is also under root. Okay, so this root cancels with this one, so we can directly write it as equals to 35. All right, so lambda plus lambda, that will be 2 lambda squared, minus 4 lambda will be minus 4 lambda, 4 plus 1, and when you move this 35 to the other side, that becomes minus 35. So we'll be left with minus 30 equals to 0. Okay, now if I divide by 2 the entire equation, so it will be simplified to lambda squared minus 2 lambda minus 15 equals to 0. So if we are to factorize this, that will be lambda minus 5 and lambda plus 3 equals to 0. So that means lambda is equal to 5 or lambda is equal to minus 3. So now we have found two possible values of lambda, so we can substitute them into the position vector of OP. Okay, what was OP? That was lambda 0 minus lambda. So I'm going to say that when lambda is equal to 5, OP is 5, 0 minus 5. Okay, and when lambda is equal to minus 3, OP is equal to 0 positive 3, because over here we have minus lambda, right? So minus minus becomes positive. Now you're not supposed to express this in column vector form. Okay, so it is better that you write it in the notation in which the original vectors are given, so which was the I and j component notation, right? I and j notations. So what I'm going to write over here is, therefore OP is 5i plus, now there is no j component, right? So I can directly write 5i minus 5k. All right, that's my first one, and this should be underlined. Or vector OP could be minus 3i plus 3k. So these are your possible position vectors. Okay, all right, so that's the end of our exam paper. I hope that if you had some issues or some problems related to any of the topics, then they will be clarified. So with that being said, stay tuned for upcoming videos, and take care. Assalamu alaikum.